Hello and welcome to my show about algorithms. I'm edA-qa mort-ora-y, and you'll know me from my other streams perhaps about Fuse and making animations and things layout. In this show I'll be talking about binary search as part of a series on algorithms, complexity, and my language Leaf. I'm using Leaf just because it's giving me an incentive to make sure that language progresses, and it's also okay to show these algorithms and explain a bit more about how they work. If you're watching and have any questions, please just ask them in the chat. I'd like to treat these as kind of an open sort of lecture. If you want to understand any of the concepts, the complexity, the code, whatever it is, feel free to just ask. And I'll try to answer. And if you want to catch me after the show, you can always go to Twitter, follow me on Twitter, or send me a message there. And I'll upload these to YouTube as well, and you can comment on that. And all the code I do today, I'll upload to my GitHub account. But before delaying too long, let's get into this, and I'll just keep talking as I'm writing. So today we're talking about binary search. I just have an empty code tree here, nothing here, but I started with a file before. So let's get this open. I'm going to go to my Leaf algorithms and my stream, binary search. I have some work done, but I'm going to start mainly in an empty file. And let me increase the font size a bit. Is that big enough? Alright, that should be good enough to see on the stream. Prevent my lines from getting too wide as well. Now, this is what Leaf looks like in short. If you've never seen Leaf before, it has this type of structure. Mostly what we're doing should be very familiar if you know any other programming language. And this is a very basic Leaf program. And I can run it over here. I don't know if I can increase the font size here. Oh, I can't, but it's all monospace, but okay, you can see it. And this program so far, it does nothing. It takes an array, and this toArray function is one I just wrote earlier today for the purpose of the stream. And all it does is convert a tuple, and this is a tuple here, into an array. And it's not a native syntax I have yet, so I had to write a function for that. And then print will just print out that array. Now first, what do we mean? What do we mean when we do binary search? We want to do binary search. Now I took the same array and I put it into big blocks over here for us. And a binary search means when you split an item, when you're searching, you keep splitting things in half. And so if I'm looking for the array, I'm going to go right in the middle and say, is this it? If not, then go to this half or go to this half. And then I keep searching downwards and I keep breaking the search up in two. So let me show that quickly what that is. If I can draw on the screen here a bit and put a few arrows here. And so I say, binary search, we say, what do we want? Say we're looking for the value 44. So we're going to first check the item in the middle. Alright, well the middle is going to split here, so we're going to go one forward, or one back, I don't remember. So we point here, and we say, is this greater than or less than 44? Well, it's less than 44. So now we don't have to look at anything over on this side. So we can exclude this entire side over here, and so this entire side will mark in red. We don't need that. And then we have the good side over here. And now we're going to say, well, let's set up the good side. Of that good side, where is the middle now? We're going to say, okay, from here, from this point here to this point here, the middle split, and we split it, and we get 44, and we say, well, this is the value we're looking for. We split it in half. Say we weren't looking for this value, then we cross off this, and we're looking for 105. So it's split it in half again, then we search here. This is the very basics of binary search. We split it in half. I just want to show you roughly how this works before getting into the code. So we're splitting in half every time. And I'll show you again what this looks like with one of the values we look for later once we have the algorithm in place. And let me just clear this all out here and close this. And then go back to the code. And I don't know where edA-qa is failing. It does that sometimes. I'll get rid of this window. Okay, so how do we write a binary search? Well, the first thing we want to do is we want to know, well, what do we want? We want the index. So our index is binary search of Q, and we want to look for the value, say, let's look for the value 2. And when it comes back, we're going to say, what do we do? Found at index. And now we have to write the binary search. Binary search. Now the initial input, we're going to say items in queue. Sorry, I sometimes forget my equal sign. Everything in the leaf is actually treated as a lambda. Functions by default don't have names. You assign them to names, and this is really good for creating anonymous names. And you notice I left a type off here. This is a strictly typed language, but it's not relevant here. We just let it use whatever type it wants. And now we're going to do binary search impl to kick it off. We're going to say 0 items dot size. This splits the search. This starts off the search. We're going to be splitting this, okay? And this still does nothing yet. Binary search impl, and I'll talk about this now. And low is an integer and high is an integer, and these are our ranges. And I'm going to be clear here now. We're going to return a value, and I'm going to be very clear about this value. It's going to be an integer, just so we know what it is, and it's going to be an integer. So we have a high and a low range. If we look at the chart, initially what we're saying is the low is over here, and the high is over here. So a 0 and an 8 will be passed in. And what we did in the graphic is we said, well, let's split this in half first. So we want the midpoint. It's low plus high divided by 2. And again, I'm actually going to keep the drawing program opened. It takes a little bit off the side there, but I can just shift this over. Okay, so we have, we said we're going to split it in two. So we have the start and the end, and we're going to take the middle. Whoops, that went weird. Okay, well. And now we said we have the low and the high. Low, high plus 2. So if this thing passed in a 0 and an 8, the middle is going to be 4. And 4 points to 0, 1, 2, 3, 4, points to right here. And be careful with the notation in computers, the plus and minus 1 we're dividing. 8 may not be a great example. It's a perfect division by 2, but it'll work anyways. So now what we want to find at the mid is this higher or lower than the value that we're looking for? Or does it happen to be the value we're looking for? So let's clear this off again, and that's exactly what we'll check in the code. Go back to here. So the key thing was says, if mid equals q, then we return mid. We're done. We've returned the index of the one we found. Okay. Now we have another special condition. Let's get back to it. So the second one now is, okay, let's calculate a new low and a new high. So we're going to have var next, and we're going to say, well, actually, sorry, not mid. This is actually items mid. If items mid, this is a subscript, so I'm saying the items at mid. If this is less than q, and again, look at the chart. If it's less than q, it means we're going to go to the right. We're going to take all the stuff on the right. And if it's greater than q, we take all the stuff to the left. So if everything to the right, now I'm just going to put an array here. We're going to start at mid plus 1 to high. Otherwise, we're going to do low, comma, mid minus 1. And we always leave mid out. This ensures we're always shrinking by 1. We never skip anything. And then we could do return binary search impl items q next 0, next 1. Those are our new low and high. And let's see what happens when we run this. I don't know why there's so many windows open for edA-qa. That's weird. Okay, and I'll kind of shift this over too. Uh-oh, it's kind of in the way now. Why is it not letting me shrink it? Come on, window. There we go. Some of these windows are a bit weird. Okay, so you can see it now. Found at 2. What were we looking for? We're looking for in number 2. We're looking for 2, and it's surprisingly located at 2. So that's not so interesting that it's located exactly at 2. So let's instead go look for the number 44. What happens then? found at 5. So we have the index, that is at index 5, is it not? 0, 1, 2, 3, 4, 5. Yes, it's at index 5. You might actually want to print this out just to compare it here and say, so Q index. Let's see if that's actually the right value. 44. Found at 5 is 44. And we can actually put it in here as well. Q at. So we found, whoops, what did I do there? Not Q, found 44. Okay, found 44 at 5, and it's 44. So we've confirmed that we found the right value. Now let's look at what it's doing. And actually, let's find a lower one. Let's say what happens if we look for, what number should we look for? Let's look for number 0. 0 is a fun one to look for. It's 0. Where is 0 found? Might get lucky in how it finds it, and we might not. We found 0 at 1, and it has the value 0. So we're looking for 0. So let's go back to our diagram here and see what that is, what happens. So what are we looking for? We're looking for the big number 0. Where is 0? And I'm going to put a question mark there. Where is 0? Now let's looking at the code again. I think I can tab over there. The first thing we do is we send low and high will take 0 in item size, and so we're going to start over there. Put it back in the mode. So this is low. Wow, that didn't work. Low, and this is high. Okay, so this is where we start. And then what we do next is we say we calculate mid is low and high divided by 2. And this is again, we have 0 and 8. So we have 0. Oh, I didn't like that. Whoa. Whatever. Right there it is. 0 and 8. And so these are the indexes, just remember that. And then we say divided by 2, and that's 4. So it's going to point right down to here. Change the color, so it's going to point here. This is where 4 is now. You can see that in yellow. Maybe I'll do it in blue as well. So blue. We're pointing there now. And then we do the comparison, and if you check the comparison again, it's items equals mid. I don't know how to temporarily clear these things, unfortunately. I could in my other screen. And we're saying if it's equal, it returns, but it's not. So if it's less than, then we use the high part. If it's greater than, we use the other part. So 0 is less than this, so it means we're going to consider this part over here. And that means we can scrub out this line here, because it's no longer there. And our new high is right here, because we said mid minus 1, so it goes up to here. Technically, it's pointing at this 12. And then we're going to split this in half again. And so half of this goes to right here. And again, it's not found, so we remove it. We take the lesser half, and we go split it down to here. Even smaller half. Doesn't like that half. And then our next middle point points to right here, because 0 plus 2 is 1, and it's going to point to 1. And then 0 equals 0, so we find the item using binary search. And we can keep doing this, how that works. And that's how binary search works. It's a very simple algorithm. And I keep opening the wrong one. But what happens if we don't find the item? Alright, well, what's going to happen here? I don't actually know. What if we put the value like 5 in it? It's not in there. Okay. And it's a segmentation fault. And the reason for this most likely is that I have a stack overflow. Because I'm using recursion here, it probably goes an infinite number of times into this binary search. That's the one right here. Because it doesn't find anything, but we don't have a terminating condition. So what we need to have here is a terminating condition. And when does it terminate? Well, it terminates in this situation if low equals high and return minus 1. We didn't find it. We're not using a failure here because a binary search it doesn't fail to not find something. It's a totally legitimate condition. That's why I'm using a return value minus 1. I might actually use an optional instead. Let's change that later. Let's just say minus 1 for now. So it's simple. And that should be enough when I say this now. Found at minus 1. Now you notice this really big ugly number here, and that's because of this indexing operation here. I'm indexing -1, which doesn't exist, and I don't have that safety protection on the arrays yet in Leaf, but it should be an error. So let's make a helper function instead here. Let's make a function that just does find 5 for us, q, 5. And we're going to make a function that takes q, whatever that is. No, we'll say the items, and then x, whatever we're looking for, and we'll print it out. And we do binary search items, x. Then we'll say if index equals 9 and 1, then standard.println did not find not equals x. Else standard println found x at index and q and items equals n, expect to say. Did not find 5. That's what we want. But what if we try it again? Now we say find q, -7. What happens? We found 7 at 0. Good. Let's try another one. Doesn't work. Q. Let's find a really high one, and also find q 105. Did not find 201. Did not found 105 at 6 equals 105. And that's the basics for binary search. We can find things, and you should test all the boundary conditions. Now we get to the fun condition of, well, what's the complexity of binary search? People like this search thing. It's a very fast search, but it requires one thing. You notice at the top here, my array is sorted. It's the only way binary search works, because if this is how the splitting works, when we looked at the graph here, it's ordered. We split it in half because when we said 31 is less than the value, well, we knew everything to the left of it we could discard. And so it depends on an ordered list. And here I'm just starting with an ordered list. You might normally want to start with, you're going to have to search the list, and I can do a quick sort one time as a way to sort the list. It's another algorithm we can cover. But for now, we're just starting with a sorted list. And so the question is, what complexity is this? How much time does this take? And that is, what is our theta here? I got to find my theta again. Theta is always selected here. Thank you. Very helpful to have that. No other character I ever get from there. So what is the theta here? Theta is equals what? We want a good theta here. There's a reason why I use binary search. And I'm just going to say, first of all, that the theta is, well, this binary search, we should put it down on this algorithm here to be clear. It's log of n. Oh, O of log n. And a lot of people have a hard time wondering, well, what does log of n mean? How many steps does it mean? And in complexity, we're saying the key thing here is we want to know how many comparisons we make. And we have to do log n comparisons. It's like for if we had 8 items, log 2 to the n here is going to be 3. We have to do 3 comparisons. But that would be log 2 to the n. So now how do we understand what log n is? And if we consider the splitting here, the way the splitting works, instead of trying to reduce what log n is, let's understand the opposite. When you take so log n, well, it really doesn't like me. Well, I'm going to ignore that program because it doesn't like me. And I'm going to go right into this text program over here. I can't, let's close this again. No. So if I go into this program here and, where's my text box? Log n equals to the n. No, it doesn't equal to the n. Sorry. If x equals 2 to the n, what am I thinking now? Oh, sorry. Oh, I'm having a brain lapse here in exactly what this is. So we have log n to the x. I just quickly write it down. I can't type these things. If x equals 2n, then n equals log x. Yeah, okay, that's the problem. Let's put it that way. Okay, if x equals 2 to the n, if n equals 2 to the x, then log n equals x. That's correct. That's what we want. Sorry for the brain delay in there. So if we look at that for a second and say, well, log n of the item is going to be x. That's like, what power of 2 is x? And this is actually log 2 of x. But we'll see why in complexity theory. We just ignore the small details of whether this is a log base 2 or a log base e, as this happens to be, and because this is technically e to the x. But let's consider the 2 to the x case was binary search. So what this means is for every iteration, and take a binary search, is that for every iteration, we can cover twice as many items. And this starts to make sense in binary search. We're saying, if we start in the text box, we say if we do one iteration, we can cover one item. As much as I like draw, I mean, sometimes it does weird things. Alright, so if we only did one comparison, we can only check one items. Now what log n means is that the moment we do 2 comparisons, we should be able to check, actually, sorry, 2 check. It's a bit weird here, it's not quite that, so let's say 2 is going to be 2 tests, and 3 is going to be 8. We can quickly jump to 8, this is actually 4, let's go 2, 4, 8. Ignore the off by 1 errors, and because obviously if you do 0 comparisons, you can't cover one item. You have to do at least once. So there's always these off by 1 errors. Well, what this means is for every comparison you do, you get to check twice as many items. And this kind of makes sense if we start looking at the block again, because we're always splitting it in half. So we split it in half, and then we compare the other side. So we've always dropped off half the items. And if you drop it in half again, you split off half the items. So every time we do one comparison, you've cut off, you can double the number of items that you've covered. And again, we covered it in half here. And I can try to make these strokes the same size so you can see that. And if there are more strokes, it's that the first one we cut it in half, we have 2 groups, the left and the right group, and then we left and right group. And so every time you do one step, you double the number of items you can take. And this is perhaps an easier way to understand what log n means, is because log n means, well, how many steps do we take for 1? You can inversely say, well, if I take n steps, how many numbers can I cover? In this case, if I take n steps, I can cover 2 to the x items. And so if you inverse relationship, it's sometimes easier to see how many items I can actually cover. And that's what log n means, is that for every step you can cover twice as many items. And that's what we do here. For every step we can cover twice as many. And every step, if we split it in half, it means the same thing, just a different way of looking at it. That's what log n means. And log n is really good because it's a really fast search. Compared to linear search, where linear search would be n, you'd have to check every single one of these things. And okay, good. So let's clear that off. I think that should be fine there, unless you have questions on that. And then that's basically I have, so that cancel that, clear that. Let's get rid of this program again. Hello, Thor. Glad to see you there. If you have questions, just ask. I'm assuming that's why you said hey. I'm assuming I said something really confusing and you'd like to know. But if not, I'm going to keep looking at your set. So O of n, this is our time complexity. It's how long it takes. Now, what is our space complexity? Put this back here. That is how much space does it take up. Now, this is a little bit about the way I've written this. I'm using recursion here, and this last function here, what it does is it calls this function again. That means for every step, it's stacking up in memory more space. Which is also really weird because that ends up meaning, I'm just going to quickly read it. It says, well, I'm very interested in what you were doing. I'm just a little lacking in knowledge of some of these things. I've been doing programming and not so much in algorithms. All right, if you have questions in algorithms, just ask. And I'm here to explain the math. I know a lot of people have done complexity in school a bit, or a bit of math, and that's but it may not be so clear, and I mean that's part of the reason why I want to do this show is I've worked with this stuff quite a bit, and I'm happy to explain this stuff for any of the concepts, and I'll try to do it a bit slower. I don't mean slower, I mean I'll just try to repeat what I've said and what complexity is. So if you don't understand what, say like what theta is, or what this big O notation is, just feel free to ask. And this is actually, I made a mistake here. That's just theta of log n. And the space complexity, as I was continuing with the stack, because I'm using recursion here, the space complexity is also log n. But this is where it gets really confusing, because technically every time I recurse, I go make one big stack into it. Okay, and I'll explain what the big O stuff means again. And as I explain time complexity and space complexity, they're both log n. So it both means the same thing. And what it means in this case is if I say log n, and that's what I was explaining with the stack, half as many items. And let's go back to O of n first, because a lot of people understand that. And that's the one they talk about in school, log n. I think the major reason we use big O as opposed to big theta I have down here is because you can't find theta on the keyboard. As you see, I always have to go to character select. What O log n means is that if I'm searching for it, the search will never take more than log n comparisons. And what I mean by that is when we go through this thing is that we have this comparison right here. This is our comparison. What I'm saying with O of log n is I'm saying regardless of how big our item set is, regardless of how big items is, we know it'll only ever take log n steps to find it or not find the item. And that's how it's stepping through, because so if we have 8 here, we know it'll only ever take 3 steps, because 2 to the 3 is 8. Again, 3 or 4, not a big difference. You always have to allow for plus or minus 1 on some of these things. So and this is the great thing about binary search, is because it splits it in half, you can think in powers. So even if you have 8 items in the set, it's going to take roughly equal to 3 steps, because it's 2 to the 3 equals 8. Or as another way, log 8, and this is exactly what log 8 equals 3. And this is precisely what it's saying. It's going to take 3 steps to find something in a structure that's 8. What if we have a set that's 100, let's say 128 in size? Well, log 128 equals 7. Again, this is log 2. Log base 2. Log base 2. These are not actually log, these are log base 2. But we're talking about complexity. We don't care about the difference between log 2 and log. And the natural logarithm is going to be close enough anyways. This in a way, this has to do with trees, and trees are a very related data structure that have the same fast one. The binary search ends up creating a tree, and if you notice, I can draw on it here again, and you'll see how it creates a tree, because when you first have a binary tree, when we do the binary search, we're starting at the middle here first, right? Pointing down to this one, and then depending on what that is, we either go to this side and search here, or this side and search here. And then we go down and search here, or we search here. And I'll just draw this tree. And this goes here, 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 here. And this is another way to visualize binary search. And you have to imagine these all mapping to a particular value. And this tree doesn't quite line up. But the binary search basically is if we're looking for the value of 2, so say we want to find the value of 2 again, so we're looking for 2, 2. We're going to say at this point in the tree, what do we find? At this point in the tree, I'm going to draw little arrows again, because these are fun. Let's pretend it's here. Is 2 higher or lower than this value? It's lower, so we're going to go to this side in the tree. Then we get over here and we say, well, 2 is on this side of the tree, and then we say it's on this side of the tree. And if you're doing an actual binary search tree, you would have this. But this is the way binary search works, is binary search basically takes a flat structure and represents it as a tree and walks down the tree. And so this is how we have Okay, I'm glad you get that. Wasn't entirely clear, but so this is how we said. You see, there's 8 items in the tree, but it only took us 3 steps to get down there, and that's because every time we go down a branch of this virtual tree by cutting the structure in half. Yes, this one relies on sorting very much. I mean, if these numbers were random, you'll just get garbage results out. I mean, I can show you that rather quickly as well here. Let's clear this tree off and leave this again. Let's go back to this program. Let's give it another array. And let's even just sort some of this. Put a 2 here, 0 here, the 12 here, put the 31 over here, and the 44 here, and then put the 200 back here, and the 105 over there. Now, let's see what happens if we start doing this. Now, you notice it didn't find 201. That's correct. It did not find 105, though it's in the list. We see 105 is in the list, but it did not find it. It found -7 at 1. It got lucky. That happens. And it did not find 5. What else might it find? Can it find 2? It can't find 2 either. And so this is where the algorithm is just going really weird. It just, because it's not a real tree, it just kind of wackily saying, okay, I don't know where it is, I'm just going randomly. It's basing it on the values. And so yes, it absolutely requires it to be sorted. So if we go back to the sorted one, then it finds all of our values again. And it does that in a guaranteed 3 steps. Again, roughly 3. Plus or minus 1, don't quote me on it. Because when we do the complexity, we don't care so much. Whether this is plus or minus 1 doesn't make a big difference, right? Like, even assume this is 3 plus 1. This would be 4. Or 7 plus 1, it would be 8. Compared to the input size of 8 and 128, nobody cares about this plus 1. And this is why we drop it off in actual time complexity. So when we say O of log n, what we're saying is that this is roughly log n, but the actual time might be. So the actual time might be log 2 to the n plus 1. So we're saying this is the actual time now. You notice it's missing that big O. There's no O there. It's just log 2 of n. This is how many comparisons it takes, precisely. But when we convert this to big O notation, we drop off these constants, because they're not that interesting to us, because they don't make a big difference. And anything with log in it, log 2, log 3, whatever, just becomes log, because it's simpler to write. And so we end up with O of log n. Now I mentioned, why do I have yeah, edA-qa. Kate, it happens to be one of my favorite editors, and one of the big reasons I like it is because I have proportional space fonts. And unfortunately, somebody pointed out to me that Visual Studio Code also has proportional fonts, so I might actually have to try it, because there's very few editors that actually work correctly with it. And I don't want a full ID, I just want an editor. Okay, so sidetracked. So what we have is we have big O is that reduction, but now I said I have theta here. And I mentioned before, I think the main reason we use big O is because theta isn't on the keyboard. Because there's something interesting about big O. Big O says, what's the maximum number of steps this is going to take? Okay, well, what if I just say n? Is this algorithm, is binary search also O of n? And let me call this t here first as well. This is the actual t of n. Okay? And this is the definition of O. O of function n, this is really weird. I can't remember how I notate this. Basically says f at n. Actually, let's do it this way. Say, what O says is that f at n always has to be lower than O of f at n. What does this mean? This is some crazy stuff here. It's saying this is an upper bound. All it's saying is that if I'm saying it takes O log of n steps, is that it can never actually take more than n steps. So this algorithm here has to be less than this one. But I can stick in n here, right? Because log 2 to the n plus 1 is definitely less than n. I can guarantee that. I could say n squared here. It's definitely less than n squared. That doesn't interest anybody. Nobody cares, right? I could actually put 2 to the n here, which is a ridiculously high number. And nobody cares about that. Nobody cares about this number. But like I say, and so what theta says is that there's a second one here. There's a omega. All right, where's our omega? Here it is. Omega. Fun, fun, fun. I think it's omega. Please correct me if I'm wrong. Omega says something else, and this one happens also to be omega of log n. And what does that mean? Well, it means our function is greater than or equal to, let's say equal to, omega of the function. Again, some wacky symbols, you can kind of forget about them. All it's saying is that omega is saying, well, this is the lowest number of steps we can take. We can't take less than this. And again, with our binary search, we have a very fixed number, log 2 to the n plus 1. So the omega of that is, okay, omega of log n makes sense. We can't take less than that. We're always going to take this number of steps. We're always going to search log 2 to the n plus 1. We'll always do that number of comparisons. Except we have the second problem. What's the problem with omega? Well, you know what? We're never going to take less than one step as well. Remember, this comparison is greater than. Obviously, and nobody cares. Nobody cares about this again. Nobody cares that we take less than one. Okay, I say nobody cares about it, but there's definitely algorithms and fields where we care about it. But when we're doing general computing algorithms, we're not really interested normally in this theoretical upper bound and theoretical lower bound. Is what we want is we want to know, well, how many steps is it actually going to take? And that's what theta means. Theta means if the big O and the big omega are the same, then it means it's theta. Okay, I hope you understood that. So basically, theta is saying this is both the upper bound and the lower bound of the function. This function will not take more than log n steps. It will also not take less than log n steps. And that's an important distinction, because if we stick strictly with big O, you can put whatever huge number you want there, 2 to the n, but nobody cares. It's obviously way less than that. So what we do is we say theta. Theta means like it's going to take at least this amount, but it's not going to take more than this amount. And it's a much more tight bound. It's much more interesting for algorithms. And the vast majority of algorithms in computing can actually be expressed in theta instead of big O. And generally, I think when we're taught this in classes and stuff, we do discuss the difference, but I know a lot of times we don't get into this difference of what does theta and omega and O really means. Yes, and Decameron, you have a very interesting point. It's like what interests you is really a matter of what you're doing. And big O does have its place, because there are some algorithms where you can't have a big theta. Right? There are some algorithms where you might know, I'm going to remove all this again. I'll leave those two. Actually, I'll leave that one. There are some algorithms where you might say, well, this one has time complexity of n squared. Big O of n squared. But you don't know. You don't know for sure. There's some complexities, and it might have a theta of log n. Right? I'm going to just take these down to the bottom here. These are some other cases, and this comes up sometimes in algorithm design, where you're like, look, I can look at my code, and I can estimate this has a loop, it has recursion, it's probably less than n squared. It's not lower than that, but it may not be. And in some cases, you're like, I don't care, n squared's enough. N squared is a horrible algorithm. I mean, that's not a nice algorithm for searching. But you might have n, and you're saying, guarantee it, I only have one loop. It might be n, but it looks like some cases it could probably be log n. And so there are cases where you don't know big theta. And generally, the most important thing here is to know is that the time complexity, you don't have to know whether it's theta or big O or alpha. This number is the most important. Just know how to count how many steps it takes. Well, this took log n plus 1 steps. How many steps does it take? That's the most important part of this. I mean, whether you can reduce it to O of log n or theta, that's secondary. As long as you can count how many steps it takes, great, you're good. That's the main thing you want to know, and you can compare them. Okay. Now, coming back to what I was saying before about space complexity. Time complexity, we said, is how many comparisons are we taking? And for space complexity, we want to know how much memory does this use. And again, we don't care about the specific amount of memory, we just want to know in what increments. And this one's recursive, and what just means is every time we call this function, it puts a bit more memory in the stack. So it has all these things that go in the stack, and this mid goes on the stack, and next goes in the stack. So at every step, it takes another small chunk of memory. And that's why it's log of n, because if it does this n log n times, it means it takes log n memory. But it said there's a small trick here. Now, you can rewrite this function not to use recursion, and we can actually do that right now. So let's rewrite this function not to use recursion. Actually, I'll copy it first because we're going to redo it. And we're going to say nr version. nr. And we want to get rid of the recursion. So what we want to do is we want to say, well, mid, high, so, and we have it here. We don't have to call this now. We can instead say, well, let's just do this. Low, comma, high equal items. And then we can just loop. And this is going to sound stupid. I'm just going to loop while it's true. For now. And instead of recursing, all we're doing is changing low and high, because that's all we have to change here. And eventually this is going to break out. And so if I did this right, I'm hoping, I just do this on the fly, I should be able to call the non-recursing version. And I get another error. Okay, where? 48. Sure. I had to put little value strips, so I don't have that feature yet. These are value lists. I don't know if this... I can explain this. It's a leaf procure. Alright. Ignore my errors. I'm going to do it this way. Var t low equals t0. There's an error there in my compiler. It shouldn't have. That should have worked. Still getting mad at me. Which is weird on line 43. My error messages are kind of weird, but that's okay. Oh, line 43 now. Loop true. Oh, I was on the wrong line. That would help. Sorry, I renamed this to while. Loop is a different condition. Right. So this still works. Ignore all my bumbling. Blah, 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 that still works. And what I've done is I've replaced the recursion with a while loop. Well, what does this do for space complexity? Time complexity is the same. We still have the same number of comparisons. But space complexity, this becomes interesting, just becomes 1. We don't have stack building up. We just have one loop. We keep using the same items over and over, so we don't have new memory. And so this space complexity ends up becoming 1. And that's actually much more desirable. I mean, the space wasn't that much to begin with, but it's more desirable to have 1 than to have more. Okay, since I was on the wrong line, I think this should work as well. I just want to check this again, because if this doesn't work, I have to fix something in my compiler, not in this code. Okay. Bad, bad, bad. Should have worked. That's why I like doing these shows in my language. Should have worked. Alright, I'm glad it was helpful, Cameron. I know not much more, I just wanted to show a bit there. And you can catch this later, I'll throw it on YouTube. Okay, so I just make these notes for myself, and I go back and I fix these later in Leaf Compiler, because I have a lot of things that should work and sometimes they don't work, but that's okay. But this binary search non-recursive one, we don't use much memory anymore. We just use this constant space and that's it, because of the fact we're not recursing. But here's where the really interesting thing comes from in a modern compiler. This thing here, it's the last call in a function, and it's calling itself. And this would be a really convenient pattern to have. And a lot of compilers pick up on this. A lot of compilers will simply rewrite this to have no recursion. And this is where analyzing something like space complexity becomes confusing here, is because technically and logically this is O of log n, but most compilers, maybe not mine right now, okay, it has some issues, most compilers will probably just get rid of this call. They'll patch up these variables and simply go back here as though you wrote a while loop. It's not quite the same as a while loop, but it'll look that way. And so basically you get a space complexity of 1 even though your code technically doesn't have it. And in some of the functional languages like Haskell, it goes way beyond doing this. It's not just tail calls, it's any terminal calls. It's quite a possibility that Leaf even does this because I'm using the LLVM backend. It's quite possible. It's the optimization is done at their level. It's quite possible this just goes away here as well. But it's not easy to confirm really quickly. Alright, so that covers binary search. I'll put some more notes on this stuff and put it online. If there's no more questions, I think that's it for today. And let me know what algorithms you want covered last time. And as I say, if you have a question, just let me know, and I'll keep answering them for next time. If you didn't get a chance to ask it in the show, if you're watching and not watching live, just send it to me on Twitter. Just follow me on Twitter, or post it to my Twitch channel. I think I can see those, or a YouTube comment on this video. And I can try to cover it in the next video or going on. I don't mind revisiting topics. And I really want to cover both Leaf and algorithms in general. Leaf isn't quite there yet to be used by people, but it's just a nice way to show this, and it forces me to find little errors like this one down here. And that's all for today. Thank you very much. Follow my channel on Twitch, and or follow my YouTube if you don't want to watch live, but Twitch you can catch on live and chat. And also follow me on Twitter, and I hope you enjoyed it, and I wait till next time. I don't know what algorithm I'm doing yet, but please tune in next time, and thank you very much.